Welcome to the nano frontier, where tiny materials are making big waves in how we control light. Today, we're talking about ferroelectric materials. These fascinating substances have a natural electric polarization, a sort of built-in positive and negative charge separation, that can be flipped with an external electric field. Imagine tiny internal electric arrows, or dipoles. Scientists have learned to arrange these dipoles into complex patterns called topological textures, especially within ultra-thin materials called nanomembranes. And this is where light manipulation gets really interesting. One major challenge has been the size mismatch. These nanoscale dipole patterns were tiny compared to the much larger laser beams labs typically use. But exciting new research has found a way around this. Scientists have successfully created dome-shaped ferroelectric topologies in freestanding barium titanate nanomembranes. Crucially, these domes are on the micrometer scale, much larger and therefore more compatible with optical applications. How do they create these unique dome shapes? It's achieved through a radial flexoelectric field, which arises from a controlled distortion in the nanomembrane's crystal structure. This, in turn, creates what are called center-convergent microdomains, where the electric dipoles continuously curl inward. This specific, continuous curling arrangement of dipoles is the secret sauce for manipulating light. When light, specifically circularly polarized light, interacts with this continuous curling of dipoles, a remarkable transformation occurs. The light becomes a vortex beam. Vortex beams are special. They have a helical, or corkscrew-shaped, wavefront and carry what's known as orbital angular momentum. These beams are incredibly useful for applications like optical trapping of tiny particles, achieving super high-resolution microscopy, and even for quantum information processing. What's even more exciting is that these ferroelectric dome topologies offer dynamic control. Researchers have demonstrated that the polar topology, the pattern of these dipoles, can be switched using heat or electricity. This means we can manipulate these vortex light fields in real time, opening up possibilities for agile optical devices. This work highlights the huge potential of ferroelectric polar topologies in nanomembranes for advanced light field manipulation. It's paving the way for new types of optical components. Creating and controlling these intricate dipole structures in thin, flexible materials is a significant leap forward. And the research doesn't stop there. Scientists are also exploring how to use twisted light that itself carries orbital angular momentum, to directly manipulate these ferroelectric structures. Using advanced techniques like in situ X-ray imaging and twisted optical Raman spectroscopy, they aim to understand how twisted UV light can dynamically modulate the material's polarization. The goal is to achieve precise, reversible control, potentially leading to ultrafast memory switches and other novel optoelectric devices. The advancements in actually making these freestanding ferroelectric films are also crucial. Techniques like van der Waals epitaxy are enabling the creation of flexible and even transparent ferroelectric devices, which could find their way into transparent electronics, sensors, and actuators. The thickness of these films is critical, and researchers are successfully creating ultra-thin nanomembranes that still retain their powerful ferroelectric properties. In summary, the study of ferroelectric topology in nanomembranes is a vibrant and rapidly advancing field. The unique physics of these exotic dipole configurations and their elegant dance with light are leading to truly innovative ways to manipulate light at the micro and nanoscale. This promises a new generation of technologies across a wide spectrum of optical and electronic applications. Thanks for tuning in to the Nano Frontier.